Utsav, you can record. Okay, so what I'm saying, Arkujit, is you people in hyperbolic geometry, they look at hyperbolic surfaces with geodesic boundary. So, for example, a torus minus a hole, right? So here the sectional, the Gaussian curvature is constant equal to -1. Okay. And this boundary, this is a geodesic. So you see the connection makes sense at the boundary points also. Does that make sense? Yeah. And
Yes.
you can make sense also of geodesics, for example, perpendicular to the boundary. So people do this, you know. I'm not sure if you can have this picture. 1 second. No, you can. It'll come out on the other side. It'll come on the other side. Yeah. So you know, the inner product makes sense at the boundary. So you can talk of angles between tangent vectors at the boundary. All right. So I mean, this is, for example, in the well-known Pant's decomposition of hyperbolic surfaces. Hyperbolic surfaces are decomposed into pairs of Pants, which are three-holed spheres like this, and these boundary components are geodesics. Okay, these boundary components are geodesics, and then you have like three geodesics with three perpendicular geodesics going from, you know, boundary component to boundary component. So here one, and say the other two will be like this and like this. Okay. And these will be perpendicular. All right.
Okay.
So yeah. So for manifolds with boundary, you can make sense of a Riemannian metric at the boundary points also, and geodesics at the boundary points. Yeah.
And this geodesic will be, I mean, if I look at the boundary manifold, then it will be a geodesic in the boundary manifold.
Right. Yeah, sure. Yeah. Yeah, I mean, here the boundary is one-dimensional.
One-dimensional, yeah.
Geodesic doesn't really make sense. I mean, this is a geodesic with respect to the two manifold.
Right.
Okay, so I mean, ddt of gamma dot is 0. Well, this is the covariant connection, covariant derivative coming from the two manifold. Okay. Does that make sense?
Yes, yes.
Okay. Any other questions? Okay. So, right. So we were talking about the Riemannian connection of a Riemannian manifold. So, yeah, okay. So we saw that without proof that on any Riemannian manifold, there is a unique connection called the Levi-Civita connection, which satisfies symmetry and metric compatibility, right? So these two properties. And so this is called the Levi-Civita or Riemannian connection. And then, of course, we saw we can localize any connection So in the first variable, we can in fact localize the connection at a point, I mean at a tangent vector. And in the second variable, we can localize it to a germ. Yes, Utsav, you were asking about this, right? So,
Yes.
yeah. Okay. And then we talked about covariant differentiation along paths. So there was a unique operator given any smooth curve. There was a unique operator called the covariant derivative along the curve, capital D sub dt, which goes from vector fields along the curve to vector fields along the curve. V goes to dv dt, which satisfied a Leibniz rule when you multiply by functions along the curve, and it was compatible with the Levi-Civita connection, right? So that means if you take a vector field V along gamma, which is the restriction to gamma of a vector field on the manifold, then the covariant derivative of V is the same as the connection applied to the vector field X in the direction of the curve, right? Okay. So this was unique. And this, again, the Leibniz rule meant that you could localize this covariant derivative. Okay, so this covariant derivative dv dt, this only depends on the germ of V near a point T, right? Okay. And then we computed an expression for this covariant derivative. And we saw that if you take a vector field V, which is say summation Vi del del xi in local coordinates. So Vi's are functions of T, which is the parameter parameterizing the curve. Then dv dt, that will also be a linear combination of the del del xi's along the curve. Dv dt was equal to the usual derivative, where you just differentiate each component of V. So you differentiate each Vk, you take Vk prime, plus a term which depended on the Christoffel symbols, right? Okay. So we got this expression for the covariant derivative. And using this, we saw that if we define a vector field V to be parallel along gamma, if its covariant derivative is identically 0, then this equation dv dt equal to 0, this becomes just a system of linear differential equations, right, in Rn for the coefficients Vk of the vector field V, right? It's just each of these components has to be 0. So that means that Vk prime is some linear combination of the Vj's, right? So it's a linear differential equation. Is this clear?
Yes.
So because it's a linear differential equation, solutions are defined, solutions exist and are defined for as long as the coefficients of the equation are defined. So, so in each chart, the solution is defined throughout the chart. And then by patching together solutions on finitely many charts which cover the curve, you get a solution along the whole curve, right? A unique solution along the whole curve. Okay. So that means that for any point T naught in the interval of definition of the curve I, and for any tangent vector V at the point gamma T naught, there exists a unique parallel vector field V along gamma such that V T naught is equal to V. Is this clear? Okay.
Yes.
So So we have existence and uniqueness of a parallel vector field given an initial vector. Okay, so this means that if I fix T naught, then I can look at this map, which is the evaluation at T naught. So let me call it phi sub T naught. This goes from the vector space of parallel vector fields along gamma to the tangent space at gamma T naught is just V goes to V T naught. Okay. So this is clearly a linear map, and this map is onto because of the existence of parallel vector fields given any vector V in this tangent space at gamma T naught. There exists a V such that V T naught is equal to little v. So this map is onto, and by the uniqueness of the parallel vector field, this map is 1-to-1, right?
Yes.
Okay, so therefore this map is an isomorphism. Okay, so that means that the dimension of the space of parallel vector fields is equal to n. Okay, so the space of parallel vector fields is finite dimensional of dimension equal to the dimension of the manifold. Okay, it's isomorphic to the tangent space at any point along the curve. Okay, and this leads us to define what's called parallel transport along the curve. Okay, so for any S and T in the interval I, the parallel transport along gamma from gamma S to gamma T, this is the isomorphism P sub S comma T, which is this isomorphism phi T composed with phi S inverse. Okay, so phi S inverse is going to go from the tangent space at gamma S back to the space of parallel vector fields, and then phi T is going to go from the space of parallel vector fields to the tangent space at gamma S. So this gives an isomorphism from the tangent space at gamma S to the tangent space at gamma T. Is this clear? Okay, so this is the picture. So here's your curve, gamma in your manifold. And what is this parallel transport isomorphism? So here's a point gamma S and here's a point gamma T. So what we're doing is the following. Given any tangent vector V here, we know that we can extend this to a parallel vector field along the whole curve, right? That means a vector field whose covariant derivative is 0. Okay. And then the parallel transport isomorphism, what it does is it takes the vector V at gamma S, and then you extend this to, you take the unique parallel vector field whose value at S is equal to V, and then just look at its value at gamma T, right? Okay. So that means V will be equal to capital V of T. Capital V is the unique parallel vector field whose value at T is equal to V. And the image under parallel transport, W, will be V, sorry, this is V at S, sorry, not T. This is V at S. So This V is Vs, and this W will be Vt. Is this clear?
Yes.
So this is an isomorphism from the tangent space here to the tangent space here. Okay. Okay. And in terms of this isomorphism, you can describe what is any parallel vector field, right? So given a point T naught in I and a vector V and at the tangent space at gamma T naught, the unique parallel vector field whose value at T naught is equal to V is just given by applying these isomorphisms, the parallel transport isomorphisms, P sub T naught comma T applied to V, right? Is this clear?
Yes.
Okay. So, yeah, okay, maybe now notice something. So suppose I fix a point. So let's suppose gamma is from an interval, say 0 capital T into M. Okay. And I fix a basis EI of the tangent space at gamma 0. Okay. And then I let Vi be the unique parallel vector field along gamma such that Vi of 0 is equal to EI. Okay, right? So then if I look at the parallel transport isomorphism, say P0 comma T, so this goes from the tangent space at gamma 0 to the tangent space at gamma T. So this is going to send Vi 0, which is EI, to Vi of T, right? Okay. And this map is an isomorphism. So that means that for all T, Vi of T will be a basis of the tangent space at gamma T, right? Yes?
Yes.
Because the parallel transport map is an isomorphism, so it's going to take a basis to a basis, all right? Okay, so you get, once you start with a basis at one point, if you parallel transport the basis, you'll get a basis at any point along the curve, okay? So it's actually convenient to write vector fields along gamma in terms of this parallel basis, okay? So any vector field V along gamma I can write as V equal to summation sum Fi Vi, right? Where Fi's are functions along the interval I. Yes?
Yes.
Now the only thing to check is that these functions Fi are smooth. Okay. So why are these functions smooth? So that's because, so first of all, note the VIs are smooth vector fields along gamma, right? Because they're solutions of a differential equation with smooth coefficients.
Right.
Okay. So the VIs are, these are smooth along gamma. These are C infinity along gamma. So that means that if I take say any VI, right? This is going to be a linear combination of the del xj's, where x1 xn is a chart near a part of gamma. Okay, x1 xn is a chart. So each VI I can write as summation over j aij del xj locally, right?
Yes.
Where the aij's are smooth functions, right? Aij, these are smooth functions on some interval j, which is contained in the interval I. Okay. Such that, I mean, the image of j lies in the chart. Okay. Now, that means that this A equal to this matrix Aij, okay, this is a smooth matrix valued function, right? Okay. Yes. But the VIs are a basis and the del xj's are a basis. So that means this change of basis matrix must be invertible, right?
Yes.
Right. So this change of basis matrix is actually invertible. So this A takes values in GLNR. Okay. Right. So that means that it's a smooth a curve inside GLNR. So A inverse also takes values in GLNR, right? It's a smooth map into GLNR also, right? Okay, the inverse matrix is also a smooth matrix valued function, right?
Yes.
And using the inverse matrix, I can write the del xj's in terms of the VIs, right?
Right.
Right. So if A inverse is equal to some Bij, then you can write del xi as summation over j Bij Vj, right? So that means the del xi's, these are smooth linear combinations of the Vj's, right? And so any smooth vector field V along gamma, this is a smooth linear combination of the del xi's, and the del xi's are smooth linear combinations of the Vj's. Therefore, it is a smooth linear combination of the VIs. Is this clear?
Yes, sir.
Okay. So therefore, these coefficients FIs,
I mean, could we also argue like this that instead of taking VI, we make it to an orthonormal form, then take the inner product because V and VI are smooth, then the inner product will be given by FIs. Then that will
sorry, say that again. I can't hear what you're saying. Sorry.
yeah, so I'm saying that like we make VIs to be orthonormal form. Okay. And then we write V with in terms of that orthonormal frame. And then these coefficients being the like it will be given by the inner product of these vector fields, right? V and VI. Then it will be smooth by because the vector fields are smooth. Can you also argue like that?
Yes, we can if we know that parallel transport preserves. It takes an orthonormal basis to an orthonormal basis. But
we have that, right? I mean,
we will have that. We will have that in a second. Yeah, we will have that. Yeah. Yeah. If we know that, which we will show just now, then yeah, you can argue like that. That's right. The coefficients will just be inner products with the VIs, and so therefore they will be smooth. That's true. That's true. But this works even when the connection is not the Riemannian connection, actually, right? This works for any connection.
Yes.
You don't need
another question.
Doesn't use the inner product in that sense, yeah.
Yeah, you don't need actually what we're doing, this covariant derivative along a curve, you don't actually need the Riemannian connection. It works for any connection.
Here we're only using the parallel transport is an isomorphism of vector spaces, not isometric isomorphism. That's what you're saying.
Exactly. It's just an isomorphism of vector spaces. Correct. Yes, Orkojit, you had a question?
Yeah, so if I look at the dual of this VI in T star gamma TM, will that be a smooth one thing?
I'm sorry, I didn't understand. What do you mean by the
So
dual
if I just take the dual, I mean, dual of VI, I mean, like if I take EI, I take the EI star.
The dual basis. Okay, the dual basis.
Dual.
Dual
That
basis,
will be
right.
smooth, right? I mean, that will also be smooth.
Yeah, that will be smooth, right. But yeah, that depends on the fact that the VIs are smooth, right?
Yeah.
So I mean, basically you're saying that, so omega I is going to be VI star, right?
Yes.
Yeah, so omega I of T, this is an element of the cotangent space.
Yes.
Right? So this goes from T gamma Tm to R. And this is defined by the property that omega I of Vj is delta Ij. So yeah, I mean, the thing is, I guess in the end, it'll just boil down to the same argument.
Yeah, that's
so
what I'm asking. I mean, I have to do the same.
Yeah. So omega I, look, you can write as some summation Cij dxj.
Dxj.
Right. And then you have to solve for the Cijs.
Right. So
I mean, the thing is, this will be a basis. And yeah, right. So yeah, the Cij will be invertible because the omega i's are a basis, right? So Cij will also be a infinity map from the interval into GL and R. It's the same argument, yeah. Right?
Yes.
And so the inverse of the Cijs will be smooth. And so the dxj's you can write using the inverse of the Cijs. So dxj will be smooth combinations of the oh, wait. No. Wait, why are the Cijs smooth? One second. Why are the Cijs smooth? 1 second. Let me just think for a second. So, okay. Yeah, so if I look at this Cij is what? This is
If I act omega I over this.
let me do it the other way. Let me write dxi in terms of the omega i's. Okay. Let me do it the other way. Yeah, the other way is better. So if I write dxi in terms of the omega i's, so dxi is say some alpha ij omega j. Okay.
Right.
Right. And then how do I get alpha I
I act dxi on vi. Vj.
exactly. So you act it on, so dxi acting on vj is going to be alpha ij. And now the vj's are smooth because they're solutions to a smooth equation with smooth coefficients, and dxi's are smooth. So this left hand side is smooth. This is C infinity, right?
Yes. Yes.
So therefore the alpha ij's are smooth, and then the inverse matrix will be the Cij's. So that is so the inverse matrix will be smooth also. Is that okay?
Yes.
So the omega i's will be smooth combinations of the dxj's, and so the omega i's will be smooth. And then of course the fi's are given by omega I applied to v, right? Your fi is omega I of v. This is what you try to do, right?
Yes. 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 Exactly.
Yeah. Okay. Yeah. That's right. That's right. But I mean, it boils down to the same argument.
Same thing. Yeah. Same thing.
Yeah. I mean, the point is that the map from GLN to GLN, A goes to A inverse, is a smooth map,
Yes.
right?
That's
map
the
is
crux of the.
Yeah, that's the crux of it. Yeah. A goes to A inverse is a smooth map from GLN to GLN. That's it. Yeah. I mean, it's a polynomial, it's a rational function, right? So it's smooth. Yeah. Okay. All right. Is this okay, Utsav?
Yes.
All right. Yeah. Okay, fine. So now that I can write V in terms of this parallel basis, why is this convenient? Because with respect to a parallel basis, the covariant derivative becomes very simple, right? What is dv dt? By the Leibniz rule, this is going to be summation fi dvi dt plus fi prime vi, right? Yes. And dvi dt, this is 0. So this just becomes summation fi prime vi. Okay. Is this all right? Yeah.
Yes, sir.
Okay, so that means what? That means with respect to a parallel basis, the covariant derivative becomes just the usual derivative. You just differentiate the components with respect to the parallel basis. Is this clear?
Right.
Yeah. Right. So, I mean, we can compute any higher order derivative also. The second derivative will be just summation fi double prime vi and so on. Okay. Right.
Yes.
And this tells us, in fact, that so if I look at this, tells us that actually we can recover the covariant derivative from the parallel transport maps as follows. So how do we do that? So okay, so suppose I take a vector field V and this is V0, okay, and say this is VT. Okay, now I have this parallel transport isomorphism, right? So this is say gamma 0 and this is gamma T. So I can use the parallel transport isomorphism. See, when I'm differentiating a vector field along a curve, what is the problem? The problem is that my vector field takes values in different tangent spaces, right? So we need, in order to differentiate it, you need something taking values in the same vector space, right? In order to differentiate. So parallel transport gives you a way to do that, right? You can identify this tangent space with this tangent space using the inverse of the parallel transport map, right? So let me call it PT inverse. Okay. So PT is the parallel transport from, oh, there's less than a minute. Okay, so let me stop here and we'll continue again. Okay, let me stop now. Okay. We'll start again. Okay, so right, so let's look at PT, which is the parallel transport from gamma 0 to gamma T, right? So if I take what does this do? This takes if I write things in terms of the parallel basis Vi, right, then it takes a vector summation Ai Vi 0 to summation Ai Vi T, right?
Yes.
Okay. So now, if I look at, say, V equal to summation Fi Vi, this is any vector field along gamma. Okay. So then, what is PT inverse of Vt? This is going to be PT inverse of summation Fit Vit. So Vit goes to Vi0. So this is going to become summation Fit Vi0, right? Yes. So that's what this vector here is. Okay, this vector is V0 and this vector here is PT inverse of Vt. Now these two vectors lie in the same tangent space at gamma 0, right? So I can look at their difference. Yes. So let me look at PT inverse Vt minus V0. Okay. So what will this be? So V0 is summation Fi0 Vi0 and PT inverse Vt is summation Fit V0 Vi0. So this is going to be summation Fit minus Fi0 Vi0, right? Okay. Now I divide both sides by t. I want to differentiate, right? And then I take the limit as t tends to 0. So this Fit minus Fi0 over t, this converges to Fi prime 0. So the whole thing converges to summation. So as t tends to 0, this converges to sum fi prime 0, vi 0, which is nothing but, as we've seen above, this is equal to dv dt at 0. Is this clear?
Yes, sir.
Yes, sir.
Okay, so what does that mean? That means the covariant derivative can be recovered from the parallel transport maps, right?
Yes.
Right? Okay. So that is another way of viewing. So instead of giving the data of the covariant derivative, equivalent data is giving the family of the parallel transport maps. If I know the parallel transport maps, then I can get back the covariant derivative by this formula, right? I just take the vector field at a point gamma t, I parallel transport it back to the initial point gamma 0, and then I differentiate in this tangent space. Okay, does this make sense? Yeah. So
Yes.
dv dt at 0, this I can write as ddt at t equal to 0 of pt inverse vt, right? That's exactly this limit here. This limit
Yes.
as t is this,
Yes.
right? Okay, so that means these are equivalent data. ddt, this is equivalent to the family of maps pt. Is this clear?
Yes, sir.
Yeah. Okay, I mean, at 0, this is the formula. At another point, basically, I mean, dv dt at some point t naught will be what? It's going to be ddt at t equal to 0. So basically, I have to look at gamma t naught and gamma t naught plus t, and then I parallel transport back from gamma t naught plus t back to gamma t naught. So what does that mean? That means I have to do p t naught of p t naught plus t inverse of v t naught plus t. Okay, does this make sense?
Yes.
Okay, so this is how you get back the covariant derivative from the parallel transport maps. Okay, so these two are equivalent data. So in some books you might find the connection given in terms of the parallel transport maps. Okay, so these are equivalent data. Okay, and now we come to the Riemannian structure. So now suppose that, so as before, Vi is a parallel basis of vector fields along gamma. Okay. And so suppose I have two vector fields now, V and W along gamma. So suppose V is summation Fi Vi and W is summation Gj Vj. Okay. So let me look at the inner product between VW. So this is going to be a sum over Ij Fij. Oh, okay. No, that's not going to help. Mm, yeah, no, actually, this doesn't help too much. 1 second. Let me think a second. Yeah, okay. All right, no. Let me just do the calculation which I have in the notes. It's a bit of a long calculation, but it's worth doing. Okay. So basically, we want to see how the covariant derivative behaves with respect to inner products of vector fields along the curve. So, okay. So let's suppose, let me just write in terms of local coordinates x1 to xn. So V is say summation Vi del del xi, and W is summation Wj del del xj. Okay. So what will ddt of VW be at say t equal to t naught? So this is summation over ij, VIWj, ddt at t equal to t naught of del del xi del del xj. So I'm differentiating this product VIWj into the inner product. So by Leibniz rule, it's VIWj into ddt of the inner product plus the derivative of VIWj. So that's Vi prime Wj plus VIWj prime into inner product del del xi del del xj. Okay, fine. Now what I can do is I can choose at this point t naught, I can choose a vector field x on my chart u near gamma t naught, such that x at the point gamma t naught is equal to gamma prime t naught, right? I can do this.
Yes.
Yeah. So then this ddt of this inner product, this is the same as the vector field x applied to this inner product, right? Yes. Okay, so this is the same as x applied to del del xi del del xj at t naught. Now I can use the metric compatibility of the connection, right? So metric compatibility says when I apply a vector field x to the inner product of a pair of vector fields y and z, then it becomes a sum. I have a sort of Leibniz rule. This becomes summation. This becomes the sum of nabla xy inner product z plus inner product y with nabla xz, right? So if I apply that, then what I'll get is nabla x of del del xi. So that's nabla gamma prime t naught of del del xi in inner product del del xj plus inner product del del xi nabla gamma prime t naught of del del xj, right? Yes.
Yes.
Okay. And now what I do is I group together terms. So so I have this VIWj into the sum of these two terms. So let me multiply VIWj with the second term here, and I'll put the Vi with the del del xi. No, sorry. Okay, what am I doing? Okay, no, wait. Yeah, so okay, I'm just collecting terms here. So this Vi into this nabla gamma prime t naught del del xi, I take the Vi inside, and then I have that times Wj inner product with Wj del del xj, and then I have a sum over ij. So I can write that as an inner product of sum over I Vi nabla gamma prime T naught del del xi inner product with sum over J Wj del del xj, right? By bilinearity of the inner product. Yeah. And then I have another term from here, Vi prime Wj into this del del xi del del xj. So here I put the Vi prime with the del del xi and I put the Wj with the del del xj. So that becomes a inner product of summation Vi prime del del xi with summation Wj del del xj. Is it clear? So those two terms will combine to give me this one big inner product, right?
Yes, sir.
Is it? And similarly, the other two terms will combine to give me this big inner product. Okay. Yes.
Yes.
Now look at this first term here. This first term, this is nothing but dv dt. V was summation Vi del del xi, right? So what is dv dt? It's going to be Vi ddt, capital ddt of del del xi, but by the axioms for the covariant derivative, capital ddt of del del xi is nabla sub gamma prime T naught of del del xi, right? Because this is a vector field in the manifold restricted to the curve. So then I know it's just given by taking the connection nabla in the direction of the curve applied to the vector field, right? Yes?
Yes, sir.
Yes, sir.
Right.
So the sum of these two terms will therefore give me dv dt. And this summation Wj del del xj, this is W. And similarly, over here, I'll get V inner product with dw dt. Okay.
Mhm.
So therefore, I get the sum inner product dv dt with W plus V inner product dw dt. Okay. So finally, this calculation gives us that ddt of inner product Vw is inner product dv dt with W plus inner product V with dw dt. Is this clear?
Yes. Yes.
So this is a sort of metric compatibility for the covariant derivative along a curve, right?
Right.
So this has many consequences. So for example, if V and W are parallel, then this tells me that ddt of VW is going to be 0, right? Because dv dt is 0 and dw dt is 0. So that tells me that the inner product between parallel vector fields will be constant. Okay.
Yes.
So now we can say what you were saying earlier, Utsav, that if I start now with oh, I didn't write it. Okay, fine. So if I start with an orthonormal basis, E1 to En, and I parallel transport it to get parallel vector fields capital EI, then the capital EIs will be orthonormal along the curve, right?
Yes.
Yes.
Okay, because their inner products will be constant. So if they're orthonormal at one point, they'll be orthonormal at all points. Okay, so then I'll get what you're saying, what's called an orthonormal frame along the curve, right? Okay. But I mean, to get that, we had to do this calculation, right? That ddt of VW, we had to do this calculation. It's not immediate, is all I'm saying, right?
Yes.
Oh, yeah, all right. So yeah, so this also tells me that in this case, the parallel transport isomorphisms will also be isometries, right?
Yes.
Right. Yes.
Because the inner product stays constant. So that means that parallel transport preserves inner products, right?
Right.
Okay, so in this picture, if I have a pair of orthonormal vector fields, then parallel transport will take them to orthonormal vector fields. Okay, so parallel transport PT from one tangent space to another is an isometric isomorphism. So of course, like you were saying, Utsav, this is only true for the covariant derivative induced by the Riemannian connection, right?
Yes.
Right. If you take a different connection, then I mean, it need not be isometries. So just one last remark about covariant derivative. You see what we're doing actually, the covariant derivative along a curve, you can think about in this way. You see, we have our manifold. Okay. And above each point, I have a tangent space, right? Like this. Tangent space here, tangent space here. So, I mean, the tangent bundle is a vector bundle over my manifold, right? And now I have a curve in the manifold. So this is the image of gamma. So what I'm doing is I'm looking at the tangent spaces along the points in the curve, right? Okay. And my connection nabla, this is a connection on the vector bundle, the tangent bundle, right? Yeah. So, I mean, you see a connection you can define actually on any vector bundle over a manifold. Okay. It gives a way to differentiate sections of the vector bundle. All right. So, I mean, actually, what is a connection? It's a way to glue together infinitesimally fibers of the vector bundle to identify infinitesimally close fibers of the vector bundle, right? That allows us to differentiate sections of the vector bundle. Does that make sense? Yeah.
Can you
see,
repeat that?
Please repeat what you said.
Yeah. Okay. Yeah, it's a bit. The first time you hear it, it's not that obvious. So look, what is a connection? So, what is a connection on a vector bundle? What is a connection on a vector bundle? It's a way to differentiate sections of the vector bundle. So what do I mean? So I have a vector bundle, say E over N, okay? Right? So a connection on the vector bundle E over N is going to be a map. So from sections of the vector, okay, maybe in the first argument should be vector fields. So it's going to be a map from vector fields on the manifold cross sections of the manifold to sections of the manifold. Sections of the vector bundle. Okay. So X, comma S, S is a section. This goes to nabla sub X of S. Okay, so this nabla sub X of S, this you think of as the derivative of the section in the direction of the tangent vector S. Do you understand?
Yes.
Yes.
Okay, so you know, this is your manifold, and this is a point P, and this is your basically you take a curve, and so here are your fibers of the vector bundle. Okay, and your section is taking values. So this is the, let's say, the 0. This is the origin of the, this is the 0 of the fibers. This is 0, 0. So your section takes some value here, and your section takes some value here, right? Okay. And now you want to differentiate the section along this direction. So this direction is the vector field X, which is a vector field on the manifold, right? So the problem is what? The section is taking values in different vector spaces, right?
Yeah.
Yes. So how do you differentiate it? Well, the connection is just a way to differentiate sections. Okay. And it's it's basically it is bilinear over the scalars. So this is, well, okay, so all right, so this is R linear in the second variable. This is C infinity M linear in the first variable. Okay. Like our connection on the tangent bundle.
Yes.
All right. And it satisfies a Leibniz rule. So nabla X of a function f times S is f nabla X of S plus xf S. Okay, where f is a smooth function on N, right? X is a vector field on M, and S is a section.
Yes.
So this will be a connection on the vector bundle. All right. Okay. Does this make sense? Yeah.
Yes.
Yes.
And now, like we proved the existence of a connection, well, I don't know if you can prove the existence of any connection on a vector bundle by a partition of unity argument. Okay, you can add local, so locally you can add, locally what happens is for a vector bundle, you have a local frame, right? Once you have a trivialization, you have a local frame, EI. And then any section S is equal to some summation AI, EI, right? AIs are functions, smooth functions on U. U is an open subset, a chart in M, right?
Right.
And you define a local connection by this nabla X of S. You just take what's called the trivial connection. You just apply X to the AIs. So you just take xai into
Yeah.
ai, right?
Hmm.
This will
Right.
define a connection. This will define a connection locally. And then you use a partition of unity to glue these local connections together, and you'll get a global connection. Does this make sense?
Yes.
Yes, sir.
Okay. So you have a connection on any vector bundle, and I mean, the space of connections is what's called an affine space. So you can take well, I guess it is a vector space. Yeah. I mean, the sum of connections is a vector space. Yeah, no, what happens is the difference of two connections is a tensor, but okay, I don't need to go into that. Yeah, so all I wanted to say is what is the covariant derivative along a curve? So what we're doing is we're taking a connection on the vector on this vector bundle Tm, right? Now, does this make sense? This is a connection on the vector bundle Tm. Yeah.
Yes, sir.
And once you have a curve, what you can do is when you have a map from a manifold to another manifold with a vector bundle over it, you can take what's called the pullback bundle. So you can pull back this vector bundle to the domain of the curve. So you get a vector bundle over the interval. Okay.
Right.
You get a vector bundle over the interval. What is the fiber over a point T? The fiber over a point T is the vector space T gamma T. Okay, so this is the pullback bundle. So this will be gamma star, upper star Tm. This is a bundle over the interval I. All right.
Right.
Okay.
Yes.
And what is a section of the pullback bundle? It's just a vector field along gamma, right?
Hmm.
A vector field along gamma is nothing but a section of the pullback bundle, right? At each point, you have a tangent vector in the tangent space at gamma T. That is the fiber of the pullback bundle, right?
Right.
Okay. And
Yes.
so what is a covariant derivative along a curve? It is nothing but it's the pullback connection, really. Okay, so when you have a pullback bundle, you can also pull back the connection. And the covariant derivative along the curve is nothing but the pullback of the connection on the manifold to the pullback bundle. That is the covariant derivative along the curve. All right. Okay. You see, I mean, for the pullback bundle, the manifold M becomes just the interval I. And, at each point, the tangent space to the interval is one-dimensional, right? It's just generated by DDT. So you just have to say what is DDT acting on S.
Right.
And S,
Yes.
your section S is the vector field V along gamma, right? So you just
Right.
have to say what is V goes to dV dt. That is the connection on the pullback bundle, right?
Right.
Yes, sir.
So the covariant derivative you can think of as it is nothing but really the pullback connection on the pullback bundle. Okay.
Covariant derivative around curves. Right?
Along curves, yeah. Covariant derivative along curves is just the pullback connection along the pullback bundle. Okay. So,
Right.
so ddt, maybe I should write this. Ddt along gamma. This is equal to pullback connection gamma upper star nabla on pullback bundle gamma upper star TM. Okay, and sections of the pullback bundle gamma star TM is the same thing as vector fields chi gamma along gamma. Okay, is this clear?
Yes.
Does this to think of it? Yeah.
Yes.
And like intuitively, what is a connection? It is a way of gluing together the fibers infinitesimally in the direction of any tangent vectors. Infinitesimally, you can identify these fibers with the, with the connection, right?
Mhm. Right.
Okay.
Mhm.
Does it make sense?
Yes.
I mean, basically, what is the infinitesimal gluing? It's the parallel transport PT where T is infinitely small. That is the infinitesimal gluing. That's what you're using to differentiate, you see? An infinitesimal parallel transport. Okay, so.
Now, if I take E equal to the tangent bundle and just put metric compatibility, I have only unique way of this identification.
And
If I
symmetry.
erase-
And symmetry.
And symmetry, yeah.
And symmetry, yeah.
Then I have the unique.
Yeah, so that's sort of a magic thing that there's a unique way of identifying these fibers, which is isometric. Basically, the metric compatibility is equivalent to the fact that the parallel transport maps are isometries.
Right. Anyway, because if you take any other connection, the parallel transport is going to be just isomorphism, but nothing about isometry. Yeah.
Yeah, right. So, I mean, yeah, so maybe I should make this remark here. So where did it go? Yeah, so for a connection nabla on the tangent bundle, okay, metric compatibility of nabla, this is equivalent to parallel transport maps are isometries. Okay. And so this metric compatibility, this is something about differentiating inner products, right? So this is an infinitesimal condition. This is an infinitesimal condition. And this parallel transport, these are global objects. So this is a global condition. Does it make sense?
Yes.
Okay, and so as usual, as in calculus, to go from infinitesimal to global, you integrate. So in this case, integrate means basically solving the ODE, the parallel transport equation. And to go back from parallel transport to the connection, you differentiate, right? As we saw, the covariant derivative you can get by differentiating the parallel transport. Okay? So it's just calculus again. You go from infinitesimal to global by integrating and back from global to infinitesimal by differentiating, right?
Yes.
Okay. That's all calculus is about, just integrating and differentiating. That's it. Okay. So, yeah. Okay. So, yeah. So the connection is infinitesimal data and the parallel transport maps are global data. Okay. That's how you can, well, that's how I think of them at least. Yeah. But they're equivalent, basically. They're equivalent. Does this help to understand? Yeah. So,
Yes.
Yeah.
all right. So, fine. So, let's stop this session. There's less than a minute, and let's start another session. Okay. Okay. So, now let's come to the next topic, which is geodesics and the exponential map. Okay. So now we can define a smooth curve gamma in a Riemannian manifold M to be a geodesic if the covariant derivative of the tangent vector field gamma prime is 0. Okay. So you see this is analogous to what we did for a submanifold of Rn, right? With the induced metric from Rn. There also we saw that, length minimizing curves, they have to satisfy the geodesic equation, right? That is the tangential component of ddt of gamma prime has to be 0, right? And the tangential component of ddt of gamma prime, that was the covariant derivative for the induced Riemannian metric, right?
Yes, sir.
Right. So now we don't have any embedding in Rn, but we have our Levi-Civita connection, our Riemannian connection, and we have a covariant derivative along curves. And so then we can just define the same geodesic equation. The covariant derivative of gamma prime is 0. Okay. So such a curve will then be called a geodesic. Okay. So, what does this equation look like in local coordinates? Okay, ddt of gamma prime is 0. So here, see, gamma prime, we're taking one derivative, and then ddt, we're taking another derivative. So this should be a second order differential equation, right? Okay. So let's compute in a chart. So suppose u phi is a chart, phi is given by coordinates x1 to xn. And suppose our curve gamma composed with the chart phi is a curve in Rn with coordinates x1t to xnt. So then that means that gamma prime t, this is summation over I, some coefficients vi of t into del del xi. And we know the coefficients have to be xi prime t, right? Into del del xi. Okay, so here vit is xi prime t, right? Okay, so now we know what is the covariant derivative of any vector field along the curve gamma. So ddt of gamma prime is going to be sum over k, vk prime, right? Plus sum over ij, xi prime, gamma ij k, vj, right? The whole thing into del del xk. Right? This is just the formula for the covariant derivative of a vector field.
Yes, yes.
Now we substitute vi equal to xi prime. So this vk prime becomes xk double prime plus sum over ij, gamma ij k, xi prime, xj prime, right? Into del del xk. So gamma is a geodesic, therefore, if and only if these coefficients are 0. So that means that d squared dt squared of xk plus sum over ij, gamma ij of k at the point x of t into dxi dt, dxj dt is equal to 0. K goes from 1 to n, right?
Yes.
Now notice, as we said, this is a system of second order ODEs, right? But be careful, now this is no longer a linear system, right? Because you have this non-linear term, dxi into dxj, right? dxi dt into dxj dt. So this is a system of second order non-linear ODEs. All right. Okay. And so nevertheless, the coefficients are smooth. And so by the existence uniqueness theorem for ODEs in Rn, since it's a second order system, we know that we'll need two initial conditions, right? The value of the curve together with its tangent vector, right? Okay. So given initial conditions, gamma 0 equal to P and gamma prime 0 equal to V in TPM, right? See, this gamma 0 equal to P, that is going to determine the values of the coefficients x10 up to xn0, right? And gamma prime 0, that is going to determine x1 prime 0 up to xn prime 0, right? Yes?
Yes.
Yes, sir. Yes.
So if I know gamma 0 and gamma prime 0, then I know x10 up to xn0 and x1 prime 0 up to xn prime 0. Therefore, by the theory of ODEs in Rn, I will have a local, there will exist a local solution which is unique given these initial conditions, right?
Yes.
Okay. So that means given any initial point P and a tangent vector V at the point P, there exists a unique geodesic gamma from some interval minus epsilon epsilon to M with these initial conditions. Okay. Right?
Right. Yes.
Okay. Now, this is a system of second order ODEs, but you would have studied in maybe even in school, you know how to convert a system of higher order ODEs into a first order system, right? You introduce new variables. You introduce new variables. So to convert it into a first order system. So here we can do the same. We can convert this geodesic equation, which is a second order differential equation. We can convert it into a, so this is a second order ODE on the manifold M. Actually, this turns into a first order ODE on the tangent bundle Tn. Okay, this will turn into a first order ODE on the tangent bundle Tn. So let's do that. So how do we do this? So first of all, note if I have a curve gamma going from an interval I into M, then we can define what's called the natural lift of gamma. That will be a curve gamma tilde mapping into the tangent bundle. So gamma tilde at a point T is going to be a pair gamma T comma gamma prime T. Okay. So gamma prime T is a tangent vector at the point gamma T. So this is an element of the tangent bundle. Is this clear?
Yes.
Yes.
And this curve projects to the curve gamma, right?
Right.
Right.
So that's why it's called the natural lift of gamma. Okay. Gamma lifts to gamma tilde. Okay. Now let us look at this lift. So recall that we had charts on the tangent bundle, a chart capital phi. Given the chart little phi, it maps a point P comma a tangent vector summation Vi del del xi that goes to phi of P comma V1 to Vn, right? In Rn cross Rn. These were our charts on the tangent bundle. So phi is given by a tuple of two n functions, x1 to xn, and then y1 to yn, right?
Right.
Map Rn cross Rn. Okay. So let's look at this natural lift gamma tilde in the chart phi, right? So it's going to be given by two n functions, x1t to xnt and y1t to ynt, right?
Right. Yes.
Now, y1t to ynt, these are the coefficients of gamma prime t, right?
Yes.
And gamma prime t is summation xi prime del del xi, right?
Mhm.
So that means that yi of t will be nothing but xi prime t, right?
Right. Yes.
Okay. So now we have that what is gamma tilde prime t. So be careful. Gamma tilde is a curve in the tangent bundle. So the derivative of gamma tilde will be an element of the tangent, the tangent to the tangent bundle, tangent space to the tangent bundle. Okay. So see, the tangent bundle has coordinates, local coordinates x1 to xn, y1 to yn. So a basis for the tangent space of the tangent bundle will be given by vector fields del xi's and del yi's, right?
Right.
So if gamma tilde in these charts has coordinate functions x1 to xnt and y1t to ynt, then gamma tilde prime t will be summation xi prime t del xi plus yi prime t del yi, right?
Yes. Right. Yes.
Now
Yes.
gamma is this okay? Yeah, Utsav?
Yes. Yes.
Yes, sir.
So now gamma is a geodesic if and only if gamma satisfies star. Star is this system of second order ODEs. Now this second order system is equivalent to the following system of first order ODEs. Gamma tilde satisfies, so the lift gamma tilde will satisfy a first order system. So here you see yi of t is xi prime t, right? So our first equation will be ddt of xk is equal to ykt, right? Okay.
Yes.
Yes.
And the second equation is this d squared dt squared. This becomes ddt of yk, and this dxi dt and dxj dt, these become yi and yj, right? Right? Okay. So this is just like what we're doing, what you did in school. You introduce new variables yi equal to dxi dt, right?
Right.
Did in school. It's the same thing that you did in school. So we're doing that here, right? So now what do we get? We get for the curve gamma tilde with coordinates x1t, xnt, and y1t, ynt. That has to satisfy dxk dt equal to ykt and dykt equal to minus sum over ij gamma ijk of xt into yit yjt, right? Now this is a system of first order ODEs in the variables x1 to xn, y1 to yn, right?
Right.
Right? This is a system of first order ODEs.
Yes.
So we can write this in the form gamma tilde prime of t is equal to a vector field G on the tangent bundle applied to gamma tilde of t. Okay, where what is vector field G? So G is going to be a linear combination of the del xk's and the del yks, right? So G at a point P comma V is going to be what? It's going to be, so look at the first equation here. I mean, the dxk dt's are equal to the yks. The yks are the coefficients of the vector v, right? Okay. So g of p should be sum over k, vk del xk plus, now look at the second equation, dyk dt equal to minus this sum. So minus this sum is basically, this is minus sum over ij, gamma ij k of p into vi vj, right?
Right.
And that into
Yes.
del y. So this defines for you a vector field on the tangent bundle, right? This is a function of p comma v, an element of the bundle. And the geodesic equation which we converted from a second order into it was a system of n second order equations. We converted it into a system of 2n first order equations on the tangent bundle. This we can write compactly as just gamma tilde prime t equal to g of gamma tilde t, right?
Yes.
Is this, yeah,
Yes.
this makes sense. Okay. So this means what? That gamma, a curve inside M, is a geodesic if and only if the natural lift gamma tilde is an integral curve of the vector field G, right?
Right. Yes.
Now, the one thing we have to be careful about, this vector field G that we're defining, this depends, a priori, it depends on the choice of chart because we're using the Christoffel symbols here to define the vector field G. And also we're using the coordinates x1 to xn, y1 to yn, right? Which depend on the choice of chart. So a priori, this depends on the choice of chart. So let me call this vector field G sub phi, right? Where phi was my chart x1 to xn on the manifold M, okay?
Right.
So G is a vector field a priori depending on the chart phi. So this is a vector field on the tangent bundle over the open set U, okay? All right.
Yes.
Now I want to see that this vector field G is actually independent of the choice of chart, okay? So if I take another chart psi on the same open set U, all right, then for any curve gamma tilde in the tangent bundle over U, so a curve in the tangent bundle, I can write as a pair, right? A curve gamma in M together with a vector field V along gamma, right?
Right.
Yes?
Yes. Yes.
Yes.
Okay. This I can do. So gamma tilde will be an integral curve of the vector field G sub phi if and only if what? If and only if, first of all, the vector field V along gamma has to equal gamma prime. So why is that? Because look at this equation, gamma tilde. So if gamma tilde is an integral curve of G phi, that means that gamma tilde prime is equal to G phi composed with gamma. And if I look at this ODE, gamma tilde prime equal to G phi composed with gamma, this will imply that this ODE means that, you know, if gamma has coordinate functions x1 to xn and V has coordinate functions yk, right? Then my differential equation is dxk dt. The first set of equations is dxk dt equal to ykt, right? So that means that the yks have to be equal to xk primes, right? So yk becomes equal to xk prime. So that means this V, this vector field V becomes summation xk prime del del xk. And that is exactly equal to gamma prime, right?
Yes.
Okay. So gamma tilde is an integral curve of G phi if and only if V is equal to gamma prime. And the second equation will then tell me that dV dt is equal to 0, right?
Gamma is a geodesic.
Right. The second equation is telling me that dV dt is equal to 0, right? Is that clear? Yeah.
Yes.
So, okay. So therefore, gamma tilde is an integral curve of G phi if and only if gamma is a geodesic and gamma tilde is the natural lift of gamma. Okay. Where gamma is equal to the projection of gamma tilde. Okay.
Yes.
But this now, gamma being a geodesic and gamma tilde being the natural lift, this is equivalent by the same argument. This is equivalent to gamma tilde being an integral curve of the vector field G sub psi, right? Where psi is the other chart. By the same argument, right?
Right.
So what do we get? Finally, we get that a curve.
So gamma tilde is independent of chart. That is the main.
Yeah, gamma tilde is just a curve in the
Mm,
tangent bundle, right?
That is the
Gamma tilde is just a curve in the tangent bundle. So what we're saying is that for any of these vector fields G sub phi defined using a chart, a curve gamma tilde in the tangent bundle is an integral curve of G phi if and only if gamma tilde is the natural lift of a curve below gamma, and that curve below gamma is a geodesic, right?
right.
So this is also true for the vector field G psi, right?
Mhm. Yes.
By the same argument, we did it for G phi, the same argument we'll do it for G psi.
Yes.
So what does that mean? That means that the two vector fields G phi and G psi, these have the same integral curves, right?
Right. Yes.
Utsav, is this clear? Yes,
Yes, sir.
right? So these two vector fields have the same integral curves. Therefore, the vector fields are the same, right?
Yes,
Okay, is this clear?
Yes.
yes, sir.
So therefore, this vector field is independent of chart. And so, in fact, we have a vector field, a well-defined vector field G on the whole of the tangent bundle, right?
Right.
Okay, such that a curve gamma is a geodesic if and only if its natural lift to the tangent bundle is an integral curve of the vector field G. Okay, so this vector field G on the tangent bundle is called the geodesic vector field on the tangent bundle. Okay, does this make sense? Yeah.
Yes.
Yes, sir.
Okay, so to summarize, geodesics which corresponded to a second order equation on the manifold, when you lift to the tangent bundle taking the natural lift, the lift becomes an integral curve of a vector field on the tangent bundle. That means the lift satisfies a first order ODE, right?
Yes.
Okay, vector fields correspond to first order ODEs, right? So okay, so on the tangent bundle, you just have a first order ODE, all right? Okay. So yeah, so to summarize, gamma is a geodesic in M if and only if the lift gamma tilde is an integral curve of G in Tn. Okay.
Yes, sir.
Okay, very good. Okay. Now let's notice something, that for a geodesic gamma, if I look at its speed, that means the norm of the tangent vector gamma prime. Let's look at ddt of norm gamma prime squared. So this is ddt of inner product gamma prime with gamma prime. So by what we proved earlier, this is going to be 2 times the inner product of d gamma prime dt with gamma prime, right?
Mm.
But d gamma prime dt is 0 because gamma is a geodesic. So this becomes 0. Okay.
Mm.
So that means that ddt of norm gamma prime is squared is 0. So that means norm gamma prime is constant. Okay.
Mm.
So any geodesic automatically has constant speed.
Yes.
Okay. So geodesics have constant speed. And now, here's an important property of geodesics, that any rescaling of a geodesic, rescaling of time gives you a new geodesic. So, so suppose gamma is a geodesic, and for a real number, let me look at the curve gamma sub a of t. This is gamma of at. Okay. The claim is this is also a geodesic. This gamma of at. So that's just a computation. So let's look at the covariant derivative d sub dt of gamma a prime of t. Okay. So that's going to be what? It's going to be sum over k d squared dt squared xk of at, right? Plus sum over ij gamma ijk at the point gamma of at into d sub dt of xi of at, d sub dt of xj of at, right? The whole thing into del xk. Is this all right? Yeah.
Yes.
Yes, sir.
Now, when you take two derivatives here, I'll get an a squared coming out, right?
Mm.
And here, when I take one derivative, I'll get an a. And here, when I take a one derivative, I'll get an a. So the product of those two a's will give me an a squared. So I'll get an a squared coming out from the whole thing, right?
Mm.
And then what will remain? What will remain is the covariant derivative of gamma prime at the point at, right?
Right. Yes.
So this will also be zero because gamma is a geodesic, right?
Yes.
So that means what? That means that this gamma A, this is also a geodesic, okay? Right?
Yes.
Yes.
So a rescaling of a geodesic is also a geodesic. Rescaling in the time variable. But what changes is that the initial position is going to be the same. Gamma A of 0 is going to be the same as gamma of 0. The initial velocity will change,
Yes.
right? The initial velocity will change. So gamma is a geodesic, and the initial conditions, gamma A 0, gamma A prime 0 are going to be what? P comma AV, right? Where PV were the initial conditions of gamma, right?
Yes.
Right? Gamma A
Yes.
prime 0 is going to be A times gamma prime 0.
Right.
So instead of PV, your new initial conditions will get P comma AV. Okay,
Right.
so the initial velocity gets multiplied by A, but you still get a
Right.
geodesic. And the point of this is, if gamma is defined on an interval minus epsilon to epsilon, then gamma sub A will be defined on the interval minus epsilon over A to epsilon over A, right? If A is positive. Yes. Okay. Yeah. So if I take A to be small enough, then gamma A I can make defined on the interval, let's say -2 to 2, right? I can make it defined on a larger interval, right? When I take A small. Okay. Okay. So now let's take an element of the tangent bundle theta naught, which is P comma the 0 vector. Okay. So this is an element of the tangent bundle. So then we know by the local existence uniqueness for ODEs or for vector fields on a manifold that we have a neighborhood of this element of the tangent bundle such that the flow phi t of the geodesic vector field is defined on this neighborhood U, right? Okay. For some fixed epsilon positive, the flow phi t is defined on the whole neighborhood U and maps into Tn, right? For mod t less than epsilon, right? This is okay? Yeah.
Yes.
Okay, now this U is a neighborhood of a element of the tangent vector of the form P comma 0. So what will a neighborhood of this look like? It will look like points of the manifold Q which are close to P, right? So that means distance PQ is less than delta for some delta, and tangent vectors so this vector is 0. So you'll get vectors nearby which are small in norm, right? Okay, so you'll get pairs Q comma V, so that Q is close to P and V is close to 0. So norm V is say less than delta, where V belongs to TQM. Okay, right? So we can get such a neighborhood U for some delta positive. Is this all right?
Yes.
Where the flow of the geodesic vector field is defined for time epsilon on the for all tangent vectors in this neighborhood. Okay. So that means basically that geodesics with these initial conditions Q comma V are defined for time epsilon. Okay, geodesics with these initial conditions are defined for time epsilon. Is this all right? Yes?
Yes, sir.
Okay. So now, okay, now if I take any theta, which is a pair q comma v in this neighborhood in the tangent bundle, so we have a unique geodesic gamma theta with initial conditions theta, right? And gamma theta of t is what? It's given by the projection to the manifold of phi t of theta, right? Phi t is the flow of the geodesic vector field. We know that when we take an integral curve of the geodesic vector field in the tangent bundle, if we project it to the manifold, we get a geodesic below, right? In the manifold. Yes?
Yes, sir. Right.
So gamma theta of t is pi composed phi t of theta. Okay. Now, gamma theta is defined, therefore, from the interval minus epsilon to epsilon for all theta in this neighborhood u of theta naught. Okay. So now let A be epsilon by 2. Okay. So then if we write A dot theta to be, so theta was q comma v, let's write A dot theta to be q comma av, right? So then the geodesic with initial conditions A dot theta, as that means with initial conditions q comma av, as we've seen above, that's just going to be gamma theta of at, right? Yes?
No, about the homogeneity property.
That's what we just saw above, right? When you rescale, the initial conditions become p comma av, right? This is the unique geodesic with these
Yes.
initial conditions, right? That's what we just saw. It's the geodesic given by rescaling by a. Okay. So gamma of a dot theta t is nothing but gamma theta of at. So that means that gamma of a dot theta, this is defined on the interval minus epsilon over a to epsilon over a. That's the interval minus 2 to 2, right? So, so geodesics with initial condition a dot theta. So a dot theta means basically the same base point q, but a much smaller initial velocity, right? Okay, epsilon is small and a is epsilon by 2. So this AV will be much smaller, that's all. Okay. So these geodesics, these are defined on the interval minus 2 to 2, right? Okay, for all theta and u. So therefore, if we let V to be A dot U, this means what? This means pairs Q comma W, where W is of the form AV, right? Where Q comma V belongs to U. Okay. So this Q comma W will be pairs of the form where distance PQ is less than delta and norm W is less than A times delta, right? Okay. Then this V is a neighborhood of the point P comma 0 in the tangent bundle, such that for all theta equal to Q comma W in V, the unique geodesic gamma theta with initial conditions theta is defined on the interval minus 2 to 2. Is this okay?
Yes, sir.
Okay, so basically by the rescaling, what we've done is given any you know, I mean, the picture is basically you have the this is P, and then we're taking the 0 vector at P, and then what we're finding is that for vectors small enough, well, and for points P, Q close enough to P. So, okay, maybe let me draw this picture better. Yeah, so if I take Q close enough to P, and I take a vector V, W at Q, which is small enough. So norm W less than A delta, and distance PQ less than delta. Okay. Then if I take gamma such that gamma 0 equal to Q and gamma prime 0 equal to W. Okay, gamma is a geodesic. Okay, so then gamma is defined on the interval -2 to 2. Okay. All right. So this geodesic with this initial conditions will be defined for time at least -2 to 2. All right. This will be the geodesic gamma. So why do we want to do this? Why do we want it defined for this time? Because now we can define for any point P and M, the exponential map based at P. This is the map X sub P. So this goes from an open set U sub P in the tangent space at P to M. V goes to gamma theta of 1, where theta is equal to P comma V. That means this gamma theta is nothing but the geodesic with initial conditions P comma V. All right, where this U sub P, this is the set of vectors V in the tangent space such that gamma theta is defined on some open interval AB containing the closed interval 0, 1. So that this gamma theta of 1 makes sense. Okay. Where theta here is P comma V. Okay. So by what we've said above, some ball of radius delta around the origin is contained in the domain of the exponential map. Right? So this map X sub P, this is always defined in a neighborhood of the origin in the tangent space. Okay. So yeah, so here's the exponential map. I mean, you have this is the tangent space TPN, and this is the origin, and then there's some ball around the origin where if I take any tangent vector V here, then what is the exponential map? Basically, I look at the point P and I look at the tangent vector V, and then I take the unique geodesic with initial conditions PV, and X sub P is equal to X sub P of V is equal to gamma of 1. Okay. Is this all right?
Yes.
Yes, sir.
Okay, so we're out of time. Let me stop here and we'll continue on Thursday. Okay.
Okay, sir.
Okay. So see you Thursday.